Good afternoon, everybody. I'm Carly Rogers. I'm the Marketing and Education Manager for IAPD. Thank you for joining today's webinar presentation, An Introduction to Thermosets. I'm happy to welcome Mark Mush as our presenter. Mark's career in the plastics industry started in 1991 in outside sales when he was working for Port Plastics. Since then, he's worked for Darmark, Roncelli Plastics, Total Plastics, and is currently the National Sales Manager for Atlas Fiber. Atlas Fiber is a longtime member of IAPD, and Mark is a volunteer member of the Government Relations Committee. Richard Welch also joins us today. He's a graduate of the Wharton School of Business from Penn and has an MBA from Northwestern. He started at Atlas Fiber in 1972, and in January 2013, he became the president of the company. Before I pass it over to Mark and to Rick for a few housekeeping items, if you have a question during the presentation, please type it into your webinar toolbar. Mark and Rich will answer your questions at the end of the presentation. As well, 1 hour after the presentation ends, you will receive a survey. At the end of the survey, there's a link to the presentation slides. A recording of the webinar will also be available to replay at a later time on IAPD's YouTube channel. Hopefully, I'll be able to get that up there later this afternoon, and then you'll receive an email from IAPD letting you know when it's up. So without further ado, I would now like to turn the presentation over to Mark Mush.
Thank you, Carly. Really appreciate that, and I appreciate IAPD setting this up for us today. Promise not to take more than 3 or 4 hours of your time during this webinar. Anyways, the presentation is called An Introduction to Thermosets, or there really isn't a material called G10 Phenolic, and that's kind of an inside joke here at Atlas Fiber. Phenolic materials were started back in 1907 by Leo Baekeland. He invented a material called Bakelite, and some of the earliest uses for it included billiard balls, which actually saved the elephants back in the early 1900s. And then you'll also see it in telephones, radios, and then on the bottom right-hand corner here, some jewelry. If you ever run across this Bakelite jewelry, it is definitely worth some money, so don't turn it away. Fast forward 107 years, and Bakelite's invention is still found in many applications in power generation, aerospace, knife handles, semiconductor, defense, the oil and gas industry, electrical equipment, and many more industries beyond that. So it's still widely used, even though it's a material that's basically 110 years old now. Here's our agenda for today. What we're going to talk about is how these materials are made, what are thermosets, the various types of thermoset materials available, the different types of shapes that they come in, tube, rod, and sheet. And then we're going to talk a little bit about the mill and NEMA specifications and how they're important, as well as downserting of materials. Then we'll talk a little bit about the common errors or misconceptions that are seen in thermosets. And then finally, we'll give you a couple case examples of how thermosets are seen in the marketplace and how you can, as a distributor, go out to those items in the market. I'm going to turn this section of the presentation over to Richard Welch, who's our president. He's way more adept at explaining the manufacturing process of laminates. So without further ado, here's Rich.
Good morning. Thank you for everybody tuning into us, and I hope we give you some information that you'll find useful. Thermosets, to use an analogy that is maybe not be a perfect analogy, but what should work is think about making a bologna sandwich. Basically, to make a thermoset laminate, you have to start by laying up layers of what's known as prepreg. In this case, let's assume we were making a glass epoxy or a G10. The prepreg is the glass cloth, a woven glass cloth. It then goes through a bath of epoxy until the cloth absorbs all the epoxy it possibly can. At that point, it becomes the prepreg. It's allowed to semi-cure, and then you start to make the bologna sandwich. You start with a stainless steel plate. You lay up as many layers of the glass epoxy prepreg as you want to get to a certain thickness. Then you put another stainless steel plate on top of that, and you slide it into this tall press that that Mark is drawing red lines on in front of you right now. Sorry, it's not a better picture on the right-hand side, but these presses can be 15 to 20 feet high and have 15 to 20 openings. Each opening is going to have your bologna sandwich in there. You then put it under pressure and heat. It ramps up to a very hot temperature, then it ramps down over a particular cycle for each kind of grade of laminate. And during that process, everything bonds together. The epoxy that is within the glass cloth all flows together, and you get a very homogeneous, solid mass that becomes your laminate sheet. It's pulled out of the press. The stainless steel plates are pulled off, and at that point it goes to a saw where the excess, which has squeezed out, is cut off, and you've got your standard size sheet, which can usually be 3 foot by 4 foot, 4 foot by 8 foot, or other standard sizes. Obviously goes through final inspection, packaged up, and shipped out. And that's, in a nutshell, that's how the laminates are put together. That's for sheet. You can also make laminated rod. Again, you would start with that pre-preg, which would be your cloth material that's gone through the resin bath. In this case, if you can imagine rolling up a window shade, that would be our analogy. The cloth, the pre-preg, gets wrapped around. You now have this steel mandrel in the middle that you've rolled everything around. And it goes into a press, which you can see on the lower right-hand corner. You set the rods in that press, and once you start to come down and heat it up a little bit, those rods are actually pulled out, and the top and the bottom of the press squeeze together, and the rod will, all that raw material comes together and gets squeezed into the rod form. Now it's like any other molded product at that point. Once you pull it out, it's very irregular, so it's got to go through a grinding process, a centerless grinding process, to get it round and within close tolerance. Once it comes off the grinder, you've got a machinable laminate rod that can be used to make any kind of standoff spacers, screws, whatever the engineer designs that your customer wants to buy from you. And that is called rolled and molded rod. Now you make tubing in basically the same way. You roll the pre-preg up around the mandrel, just like rolling up the window shade again. You pre-cure it by putting it in an oven and then in the press where it squeezes down the same way, only in this case you do not remove the mandrel while the material is being cured in the press. You leave it in. After it comes out of the press, it goes to a machine called a tube puller, which mechanically yanks that mandrel out of the center, leaving you with a hole that goes through the middle of the rod, and voila, you've got a tube. Once again, the outside diameter is a little rough, so it's got to go through a centerless grinding process, at which point you've got your finished product, and again, make it into whatever that engineer has designed on the blueprint. Here's just another view of a rolling machine for tubing, where you've got the pre-preg, or we call that sometimes the B stage, goes through a series of rollers to take the tension out of it, and then gets wrapped around the mandrel, goes into the press, goes through the press process, and what you get at the bottom right corner there, that's a finished product of a machined part that's been made out of tubing. I'm going to turn this back to Mark for the time being, and we'll be here to answer questions after we're all done.
Thank you, Rich. Many of you in the plastics industry are mostly experienced with extruded or molded materials, so the manufacturing process for laminates is obviously way different. And this presentation is going to be sent to you later on, so you'll be able to take a look at that. And if you have any questions, definitely, like Rich said, we'll answer them at the end or call us later. So anyways, once this material is made, it's got to meet certain specifications to be called that. And I put on here in the green section here, you just can't spray paint some plywood green and call it G10. And basically what that means is there's a couple different specifications that we go with. The first one is the NEMA grade, which stands for National Electrical Manufacturers Association. That's probably the most common term that you've seen out there. You'll see the XX, the XXX, the CE, FR4, G10. And then next to that is the mill specification, which all has the standard mill I 24768 with a slash number that distinguishes what that grade is. And then the third column there is the type of the material. I always like to point out that when a material is called out by the mill spec And for example, let's use which is the /2 here. You cannot substitute that. If you have a print that says mil I24768/2, definitely go with the mil I24768/2. You cannot substitute a /27. We'll talk about the differences between the G10 and FR4 in a few seconds here. So basically, in order for a material to be called G10, G11, phenolic, et cetera, it has to meet those mil spec, the NEMA standards for things like specific gravity, tensile, compressive strength. If it doesn't meet those specs, you really cannot call it a G10 or a G11 or phenolic, for example. And we're going to start with the first material, which is FR4/G10. It's a glass epoxy material. This is probably the most popular material out there, and it's probably the most well-known. If anybody says glass epoxy, they're going to say G10. This has got some tremendous electrical characteristics, which are exhibited over a wide range of temperatures and humidity. I'm not going to read each one of these for you, but like I said, you'll have this. One thing you might want to keep in mind is there is no shelf life limitations, although we kind of recommend up to about 10 years in proper storage. And then the temperature on G10 goes up to about 284 degrees F. And the bottom left-hand corner, you'll see some typical applications for this material: terminal boards, structural parts, insulators, rollers, that type of thing. On the right-hand side is obviously a G10 part that's been made. G10 or FR4, what's the difference? This is probably our most popular question that we get, and we obviously made this slide a long time ago to answer those questions. I'm going to read the top line for you. FR4 has the chemical element bromine, which is a halogen, or some other non-halogen materials, which acts as flame retardant additives. And flame retardant is obviously the key word there, and gives you the FR and FR4. This material is not fireproof. When I emphasize again, it is not fireproof. It is flame retardant. It will burn, but it will self-extinguish. It is rated UL 94VO. Plain G10 does not have any flame retardant chemicals whatsoever in the formula. It has a different UL rating, which is the 94HB. And then again, the specs here, the FR4 has the /27, and the G10 has the /. If the mil spec is called out, once again, you cannot substitute one for the other. But you can go the other way. If G10 is called out, you can substitute FR4 for that, but not the other way around. Just the glass epoxy, the NOI 24768/3. There's a nice little G11 part there for you to take a look at. It's a grade very similar to the FR4 G10, but is definitely suited for higher temperatures. It goes up to 356 degrees Fahrenheit versus the 284 degrees of the G10. And your typical applications for G11 is an application where G10 just doesn't meet the temperature requirements. That's probably your most common application for that. And because it goes up to a higher temperature, G11 does see a higher cost than G10. G7 silicone. This is the highest heat laminate. It goes up to 428 degrees F or 220 C. This has got some great high heat or arc resistant application capabilities. And in certain circumstances, you can go up to 500 degrees F. We typically like to say that G7 is going to go in an application where higher temperature ratings are needed, such as a heating or an appliance insulation application. And there's a sample of some G7 in your bottom right-hand corner. G9 glass melamine, which is one. This has the best arc resistance and dielectric properties. It's great for radio frequency heat sealing. It's also commonly used as a substitute for G5. We commonly see requests for G5. G5 is a much more difficult material to obtain, so we typically will substitute the G9 for that. A lot of your applications for G9 will include arc barriers, structural parts, welding applications, circuit breaker components. So if you have customers that you're targeting in those industries, I would definitely make use of the G9 material. Okay, there's three types of phenolic: paper, linen, and canvas. And I'm going to bring up three pictures really quick of the different materials. A couple tips on phenolic materials. The XX is a mechanical application for paper. The XXX is your electrical grade. And that's typically seen in the cost as well. XXX is about 50% more than paper, although paper overall is your least expensive material in the laminate family. The E, which you see on the left-hand side for both linen and canvas, stands for electrical grade. If you just see the C or the L by themselves, that means it's the mechanical grade. And here's a nice question. If you look at those three pictures here, they all look the same. How do you tell them apart? Well, we're here to help you on that. Paper phenolic, in this blown up picture, it's very easy to identify because it's got the very smooth finish or texture to it. And then some of the applications for paper phenolic typically, and their punch parts in mechanical grade, jigs, templates, washers, in something in high humidity applications, a very good part for water absorption is a issue. In electrical grade, low power apps, switchgear, oil-filled transformers. Linen phenolic is very easy to identify because it's got a very fine weave or finish to it. If you notice in the box there, it's got that very fine look to it. And then some of the applications for linen, they both differentiate between mechanical and electrical grade. Obviously, mechanical grade, you're going to go more gears and terminal boards. Electrical grade, you're going to see it more in an electrical application. And then finally, canvas phenolic. If you notice the difference between, going back here, the linen phenolic's got that very fine weave to it. Canvas grade, when you see this in the field or at a customer's location, get that very coarse weave to it. So if you see that, that's obviously a canvas material. And then once again, there's mechanical and electrical options for canvas phenolic, gears, spacers, structural parts, pulleys on the mechanical side. And then for the electrical, just say there's many applications for electrical where the electrical and mechanical properties are needed. Yep, insulation is a very good one. This is something that we see quite a bit, and the football draft yesterday was kind of timely on this. If you're thinking about downsorting from CE to C, as former coach Lee Corso says, not so fast, my friend. We like to point these out because there's sometimes people will sit there and try and substitute the CE grade for the C. And if you're just looking at water absorption, okay, that's great because the CE actually has some better properties in water absorption than the C. But when you start getting down into the flexural, the tensile, the izod impact strength, you see some very noticeable differences there. 17,500 versus 18,000, 11,000 versus 12,700 in the tensile strength. That's more than 10% on that. And what we like to say is, do you want to take the chance that your customer really needs that C capabilities of this higher end here? And if this is substituted, look at the difference there. You're going to have 11,000 PSI versus 12,700. Same thing in the izod impact strength. And bonding strength especially is really wide open here. The C is a mechanical properties. This is a mechanical grade material. The CE is a electrical grade. And then the same thing literally applies to LE versus L. Once again, the LE has some better water absorption capabilities, but the same thing, the flexural strength, the tensile strength, the izod impact strength, bonding strength. The L material is much stronger than the LE, which is obvious. It's a mechanical grade versus an electrical grade. And then if you look at the compressive strength, this wasn't seen on the C versus CE comparison, but again, the LE can go up to 36,000 PSI versus the L 8,000. Again, if your customer is looking for, say, 37,000, you want in this material, not that material. So the thermoset shapes. This is pretty basic. Sheet, tube, and rod. And then sometimes we get call-outs for hex rod, but hex rod in thermoset materials does not exist. So we put that little. You can machine it, but it's not a standard material. So then there's your sheet, there's your tube, and then there's your rod. Basically 3 forms. What to look for in sheet. As Rich mentioned earlier, typical sheet sizes are a 36x8, 4x4s, and 48x96s. And they typically go anywhere up to 6 inches, depending on the material, of course. Now, this is really important, and when we do presentations with the people, we always like to point out this. NEMA tolerances for thickness are very wide open. I've put an example here of if you're looking at 1/8 or 125 G10 sheet, the tolerance on that particular size is plus or minus 12 thousandths. So basically, that material can come in at 113 up to 137. So if you're at a customer and your customer is a machine shop, for example, and they say, hey, I need to get some G10 1/8 inch for a project I'm running, ask your customer, what is your finished thickness size? And if he says, hey, my finished part is at 125, you're going to have to go up in size up to the next size to make sure that he gets that, because otherwise you will send in some material, 125, he gets it, he's going to call you back and say, hey, this material is measuring out at 115. That's intolerance. Really the best way to achieve those tolerances, if you need them, is to sand that material down. That way you can provide a customer a finished part or material that's pretty close to his finished size. Saves them some money and also saves them some machining time. Again, the standard mill spec, mill I 24768. Tube. Every tube out there is made to order. There are no typical sizes. Everyone is, like I said, is made to order. Expect longer lead time when you're dealing with tube. And the typical sizes, or the lengths, range from 36 to 48 inches long. There's a standard mill P79 cert for that versus the mill I 24768, which you see in the sheet materials. And generally, there's no concentricity call out for tubing, so be careful of what you're looking for or what you're getting on that material. Finally, rod. There's two types of rod. Rich showed you the process for manufacturing molded rod. Sheet rod, kind of like what its name sounds like. It's material that's made out of sheets, typically cut into strips and then turned and ground into some precision rods that you see on the right-hand corner there. The difference between molded and sheet rod is sheet rod has definitely a lot tighter tolerances. You can see that the 1 1/4 diameter, the tolerances are plus or minus 1/1000. Anything 1 1/4 to 3 inches in diameter is plus or minus 3/1000. And then anything over 3 inches in diameter, your tolerance is plus or minus 5/1000. And sheet rod diameters typically go up to about 6 inches in diameter. This is one of my favorite slides that I do in presentations. A lot of people ask the difference between molded and sheet rod. And it's very easy to identify. Rich had already mentioned this rolled up window shade look. So if you have an application, you're out in the field and you see a piece of material and it's got this rolled up look, it's definitely sheet rod. Excuse me, molded rod. Thank you, Rich. And if it's got this flat look across it, that's a sheet rod. And another way to identify these, if they're in the field and you, for some reason, you can't look at the bottom, molded rod's typically 46 inches long, and sheet rod is 48 inches long. And molded rod's going to work better than sheet rod in tubular applications due to its circumferential lamination pattern. It basically holds up to pressure all around the rod versus the sheet rod. Here's some common errors that are seen in thermosets. Can I get a quote on G10 phenolic? That was the title of our presentation. This is one of the most misnamed words out there, call-outs. There's no such thing as G10 phenolic because they're basically two different materials. G10 is a glass-based material. Phenolic is a phenolic or cotton-based material. Or somebody calls you up and says, I need some micarta, or it's on a blueprint. Micarta is a trade name. That's like going into a, saying you want a car, and what kind of car do you want? I want a Ford. Well, what type of Ford do you want? So if you ever see that called out with your customer, you're going to have to call them back and say, hey, what type of, are you looking for a phenolic? You're looking for a glass epoxy material? And then where do I find Bakelite? This is an obsolete trade name. Unfortunately, the Bakelite name hasn't survived the 107 years since Mr. Bakelin founded that material. And you will also find that there are lots and lots of other old trade names and call-outs that are just long obsolete. So that's something you have to keep an eye out for. Does this come in hex rod? If there's no hex rod, it can be machined, but it's not a standard. It's not a standard material like the rod that's in molded or sheet rod form. And then finally, we came up with the typical question here: plus or minus 5/10,000. You can probably machine down there, but it's pretty borderline. It's not like a Vespel that you can machine to some really incredible 1/10 tolerances. It doesn't go that far. And even in the plus or minus 5/10,000 example here, that's pretty open as to whether we can get that or not, or any machine shop can get that. And again, this material cannot be broached. So here's an example of a print that we've seen in the past. It comes out with the broaching right there. Can't be done. Again, right there. Here's a nice call out that you'll see. They're calling out hex stock. Again, this is not a standard thing. So the material call out is FR4 epoxy glass, but they're calling out hex stock. Again, that's something you can't get. So if your customer hands you a print with that, you might want to immediately return it back to them and say, this material is not available. And then here's a nice one here. We talked about the generic. So your customer's print has material, micarta. Once again, is it canvas phenolic? Is it linen phenolic? Is it G10? Is it G11? If you ever get this from your customer, what grade are you looking for? Okay, so what we've done is that kind of covers the material. So I'm going to go over 3 case studies taking these materials into the marketplace. And being in sales for a long time, having worked at several machines, showing where these type of materials go, as a distributor, if I was looking for some new opportunities, the first place I would go is go to a machine shop. Target your local machine shops, converters. And the why? Well, number one, they're very easy to find. You're probably already doing business with them. The decision makers are much more easier to get a hold of and talk to in person versus going into IBM or General Dynamics and saying, hey, are you guys using G11 here? The machine shop, you walk in, you talk to the owner of the machine shop, you might talk to the machinist or who's buying the materials. Much quicker and a lot easier than getting into the larger OEMs. What type of materials are they using? Well, they're probably using pretty much every type of thermoset material out there. FR4, G10, G11, G7, G9, Phenolic, some other laminate materials. They're probably using the thermoplastics materials like Delrins and nylons and Peaks and Ultems that you're already selling them. What you need to do is just ask, are you guys machining G11? Are you machining G10? And some tips that I've come up with having many years experience working for machine shops is definitely know those NEMA tolerances that we talked about, especially those flatness tolerances. If a machinist is working on a part, and we'll use that 1/8" example of the G10, and their finished part is 125 in G10, they're not going to get that. They're not going to get that in that grade. So know those tolerances. Know the difference between G10 and FR4. If your machinist is calling out, hey, I need some G10, maybe they can use FR4, but maybe they're getting that spec that says they've got to use the /2 versus the /27. And then the third tip there, if a machine shop doesn't touch that stuff, that's a term I've heard many, many times. We don't machine that stuff. I don't like to deal with that stuff. None of my guys like to touch that stuff. This is a selling opportunity for you. Ask them if you can machine the parts. I know that a lot of you have machine shop capabilities yourselves, or you send that type of work out. A machine shop might get 20 prints from a customer. 15 of them are Delrin, nylon, and Peak parts, and 5 of them are G11, for example. They may be no quoting those 5. If they're no quoting those, they're obviously not going to sell them that material. So ask them if you can quote those 5 parts for them. You're not only going to increase your sales, but you're going to help your customer out at the same time. And then finally, ask about phenolics or glass epoxies by name. And this is another perfect example from past experience. I would call in customers in the past and say, hey, are you guys doing any parts made out of G11? And I say, I'd say, are you guys doing any plastic parts? No, we don't do any plastic parts. Ask, are you doing anything out of G11? Because I knew they were. Oh, yeah, we do all the fiberglass all day long. So ask specific names. Ask about G11. Ask about G10. Ask about phenolic. You'll be surprised in some of the answers you get. And then applications at machine shops, believe me, machine shops are machining parts for everybody. It can be from a washing machine to the space shuttle or a rocket or computer equipment. So to me, it's the first and natural choice to go to sell thermoset materials. Second is aerospace and defense companies. Probably across the country, you've got to have a local aerospace OEM, somebody in the defense industry, or somebody who's supplying to the aerospace and defense industry. Those are more targets that you can call on. And why? Aerospace has long been a traditional user of thermoset materials. They can take temperatures. They can insulate materials. They're very sturdy applications for structural parts. They're lightweight versus metal. And again, same type of applications, FR4, G11. It runs the gamut of all materials there. Some sales tips I always like to pass along for the aerospace and defense industry. I talked earlier about some old specs. Aerospace parts, typically when they're spec'd in, do not change. If it's I've run across many applications with the Navy, and a specific manufacturer had gone out of business, and the guy told me, hey, I need to get this material. I said, the company's out of the business. You're not going to get that material anymore. The guy told me, Congress literally to change these prints. Eventually they were able to print, but keep in mind there's a lot of old specs, a lot of old trade names out there. I've seen prints from the late 40s, the 50s, early 60s that call out laminate materials. They are out there. And again, as with machine shops, You have your aerospace and defense companies. A lot of people don't like to machine thermosets. It's a very abrasive material on your equipment, your cutting tools. Again, an opportunity for you to go into a customer, potential customer, and say, look, we can machine those G11 parts for you. We can machine those phenolic parts for you. You make much more money selling parts than you do flat materials or a rod or tube. Always do, it's much better to sell a finished part than just the sheet material. Some typical applications, braking system. We talked about structural parts for floors, walls, window frames. Insulation. Insulation is a common theme in this material. It was invented for electrical insulation. It's a great thermal insulator as well. And then finally, the final case study for market to target, power generation. Generators, transformers, power plants. And the why? They're generating high voltage and high levels of electricity. They demand insulated materials for both electrical and thermal elements in this industry. I would say this is probably the largest generator, and I'm sorry for the pun there, of thermoset applications in the country. Some of the more common materials, you're definitely going to see the higher end materials. You're going to see the G10s, you're going to see the G11s and G9s. Some quick sales tips in the power generation industry. Basically, if a company's generating electricity, it almost certainly will have a need for thermosets in there. And because they're generating high amounts of electricity, they're generating high heat, they're typically going to demand a higher performance material like the G11s, the G9s. They're not going to use a GPO3, which is more of a commodity item. And then some of your applications in that industry, components that must have high compressive, flexural, and shear strength. They require low creep and retain their electrical insulation capabilities at continual high temperatures. And again, key words there. High temperature, electricity. Those power generation, there are lots of materials in that industry. Finally, here's kind of a review of the laminates that are valued in the marketplace. We've talked about their high mechanical properties. They've got great electrical insulation. They've got great thermal insulation capabilities, low moisture absorption, flexural strength, compressive strength, the same thing. They're very, cost-wise, they're much lower than, for example, PEEK. And then on the right-hand side, this is what I like to call an area for generating new leads. We talked about machine shops. We talked about aerospace and defense, and we talked about power generation. Those aren't the only three industries that are using this. Semiconductor, SAIC code 3825. Switch gears, 3613. Knife handles is a huge and growing market. It's amazing how many people are using G10 on their knife handles these days. Welding equipment, we talked about that earlier. That's high temperature. Transformers, 3612. If you have a SAIC code directory and you want to start going after the thermoset market, 3612 is your starting point there. That should be number one. Transportation and X-ray tables. So that gives you a kind of a wrap-up on the value of the marketplace and where to sell them. And that concludes our presentation with our famous thing. But we would definitely at this time like to thank IAPD for arranging this. We've long been a member of IAPD, and we definitely appreciate doing business with the IAPD. So we're going to open this up to questions.
Thank you, Mark, and thank you, Rich. We do have a few initial questions here, so if anyone has any further, if you want to send those in, and they can get them answered for you. But starting off, going back to some of the beginning of the presentation, what is the lower temperature limitation for FR4?
Well, there are cryogenic grades made that will go down to the super low temperatures without outgassing. That's the main reason that they're used as the outgassing process. So they're not going to create any problems when you do take them down to those temperatures. But in fact of the matter, neither the NEMA nor the military specs will call out a low temperature limit. So we all, for many, many years, have been flying a little bit blind on that, and it's a great question because there's no specific answer for each material as to how low it will perform. Again, if you've got to have something that's super low, you're going to have to go with a pure G10 or a cryogenic G10. That'll take you down the lowest.
Okay, thank you. What is the advantage of using G10 over FR4?
Again, it's non-brominated, And so it will not outgas when it gets into certain applications. It won't outgas when you're machining it. It won't outgas at very low temperatures. So it's in that way chemically slightly more stable material. The advantage the other way with FR4, of course, is you've got the flame retardancy.
Okay. What is the cost of G7 versus similar heat-resistant materials such as PEEK?
Another good question that's a little hard to answer right off the cuff, but I would say pound for pound, G7 is probably going to be slightly more expensive.
Okay. How did a 3x4 become a standard size for G10 and the phenolic sheets?
Well, it actually goes back to the cloth that's used for all these laminate products. The cloth itself, industry standard to weave the cloth somehow, some way, was standardized at about 50 inches wide. So everything that goes through the treaters and the presses starts out at 50 inches wide. Now, from there, you can go as long as you want, but you are limited by the size of the press that you can build. The earliest presses probably were meter size. 39 inches would be the standard, but in the U.S., 3x4 just became the standard size because that was an easiest size to build the press to. Then it expanded, and the largest is actually, I think in the States you can go to 120 inches long, but generally speaking, 8 foot is the longest. But for the standard sizes, the 48-inch comes from the width of the cloth. Everything else is based on what's the most efficient press size that they can build.
Okay. Is there centerline porosity with the rods?
In rolled and molded rods, I would say you could say yes, there is some porosity. You can't get as much pressure on these in the press, and as that material squeezes down towards the center, you definitely get a collection that is heavier in resin than it is in the main material, the cloth that's in there. Also, in molded rods, as you get up over 1 inch, you can see some radial cracks in the interior because as it comes out of the press, the inside of the rod is cooling at a different rate than the outside. And that difference in cooling rate can create some stress fractures in there. When it comes to sheet rod, you won't see any of that. You will get no voids, no porosity, because that rod is taken from the sheet stock that has been pressed, squeezed down under immense pressure. You're starting with that homogeneous massive material, and when it's cut into square bar and then centerless ground into round bar, you're maintaining that homogeneity. So that's probably the main advantage of the sheet rod to the molded rod. You're not going to see any of those internal cracks.
Okay. This question is, I think, going back to the aerospace case. I know that there was one line, I think, in the tip that said A&D companies, and Mark, I think you said it, but they just want clarification on what the A stood for.
Aerospace and defense.
Aerospace and defense. Does any of the phenolic grades degrade when submerged in water? And then they have delaminate in parentheses.
Delaminate.
I think that it'll certainly degrade faster than it's just out in the general atmosphere. Let's say for paper-based, canvas, and linen, the phenolic grades, I would say, would be affected more quickly than any of the other grades. However, the term used was water, but if you expanded that to other fluids such as transformer oil, it turns out that the paper-based grade is a terrific insulator within oil-based transformers. So it depends on the fluid that you're talking about. But in general, yeah, I don't think I would want to put a phenolic part, canvas, linen, paper, submerged in water unless it was a specific specialty grade like the canvas marine grade, which can take very high humidity applications. But again, to be submerged in water, probably not the best application.
Okay. Should special safety or respiratory measures be taken for the machining process?
No more than your regular exhaust systems for sawing. You definitely want to get this exhausted as quickly as possible, just like any other sawdust that you'd be creating. But there are no specific hazardous health issues associated with any of these.
Okay. Are G3 and G5 still available?
G3 actually is becoming a very popular product after years of being more of a specialty grade that you didn't see very much of. Its flame retardant characteristics and high heat characteristics are making it in demand for the aerospace market. So you're going to see a lot more of that. G5 has kind of fallen by the wayside because all of the properties are exceeded by the G9. They're both glass melamine grades, but the G9 characteristics pretty much cover all the G5. So G5, you're probably not going to find on anyone's shelf at this point, but if you have to have it, yes, it can still be made.
Okay. If molded rod and sheet rod are both ground, why does sheet rod have a tighter tolerance?
I would have to say that goes to the manufacturer. Yeah.
Okay. Why can you not broach thermosets?
Unlike a thermoplastic that is somewhat pliable and movable, and you can squeeze it under pressure, once you've made that thermoset, it doesn't move very well. And if a broaching operation is a displacement of material, so it would be like trying to broach something that was very, very hard, and you'd wind up just destroying the material. Unlike trying to put a broach in a piece of nylon or Delrin, where it's going to actually push that material out of the way and create the form that you're looking for, it'll probably fracture a thermoset if you try to do that.
Okay. Let's see. What is the price difference between rolled rod and sheet rod?
They are reasonably close at this point. It used to be that molded rod was quite a bit cheaper, but labor factors, when you consider that each molded rod has to be rolled up one at a time, similar to tubing, as labor costs have grown, those have become very close to each other. So I wouldn't say that there's a great price advantage one way or the other.
Okay. Going back to one of our previous questions that was asked, I think she wants just a little bit more clarification for what's the difference between G10 and FR4. What does non-brominated mean?
Well,
or if we could have a little bit more clarification to it.
Sure. As Mark explained, the FR in FR4 means flame retardant. In order to become flame retardant, there is a chemical called bromine added to the mix. The pure G10, as opposed to the FR4, does not have any bromine in it. So we call it non-brominated. It used to be for many, many years that FR4 was far and away 99% of the market. If somebody said G10, we just kind of took it for granted that they really meant FR4. I would say over the last decade that has changed fairly dramatically, and that the use of the pure, true, or non-brominated G10, any way you want to call it, but just regular old G10, non-brominated, is probably now 15 to 20% of the marketplace. And the brominated, or the flame retardant, the FR4, is the balance of it. Still more popular, but you'll see the true G10 growing more and more all the time.
Okay. Are the glass grades good with water?
It kind of goes back to the previous question.
Yeah.
What's the best in high humidity situations? I wouldn't say that any of these products really you would want to use them in submersible applications. They all hold up reasonably well to high humidity, but to submerge them in water for an application, I probably wouldn't want to see a design like that.
Okay. Are there grades specifically recommended for outdoor applications, possible UV stabilizations?
In general, these grades are not UV stabilized. For example, if you put a few sheets of canvas phenolic on a shelf in the warehouse, and one of them's an inch or two of the surface of one of them is exposed, and you go back a few weeks later, you're going to definitely find a color difference that has darkened up. And these do darken with age. You would have to go, I think, with a black material to get more of a UV stabilized result out of it. And again, these are okay for outside applications. In general, it's just to take them all as a blanket statement. But G10, the glass grades probably are going to weather a whole lot better than a phenolic grade, whether it be paper, linen, or canvas outdoors. But again, they're not UV stabilized.
Okay. I might butcher what this says. Do you have any experience with frac balls? How do G10 frac balls compare to Torlon 5030? Are there any advantages?
I would say that the frac ball market is pretty well past G10 and G10 FR4 by. It was a hot market for 3 or 4 years, but they're going to many other kinds of materials now, including some materials that are being imported that will, dissolve on their own at a certain point, so you don't have to go down and drill them out. Yeah, G10 and FR4 was a great market for frac balls for a few years. Grades like Torlon and some other materials seem to have eroded that market quite a bit. We don't see a whole lot of demand for that now.
Quick point on that too is the frac ball market was kind of a victim of its own success. Obviously, they frack for natural gas and oil, and they've actually driven the price down so much that they've stopped doing it in some areas. And then originally it was just 3 or 4 companies doing all the fracking, and everybody saw the tremendous amounts of money that they were making into it. And 25 or 30 other companies got involved, and they basically commoditized it. And then, like Rich said, so they commoditized the G10 part of it, and then eventually they just switched to some other materials so G10's hardly even used anymore.
Yeah, you may find some smaller manufacturers that are still making sets of frac balls out of the laminates, out of the G10. But they're definitely trying to find lighter materials that they don't have to drill out, that are going to self-dissolve.
Okay. Why would someone use rolled over sheetrod, rolled rod over sheetrod, or vice versa?
The main reason to use a rolled rod, again, is because the strength is around the circumference. So what I always try and say is, if you're looking at a machined part that conceptually you say, boy, it looks like that should be made out of tube, that shape is what the rolled rod is really used for. When you're going to bore out the inside and leave yourself with a very thin wall, the rolled rod is going to be much stronger than a comparable part made from sheet rod. To me, that's really about the only time that molded rod has a significant advantage. All the other advantages would flow to sheet rod.
Okay. What are applications for washing machines?
They could be bearings, gears, standoffs. The circuit board that's in a washing machine is going to be made out of FR4. Take it apart, you're going to see a lot of those.
Okay. They say that they've run into color variances with the laminates. The mill spec is vague, giving a broad range of what is acceptable. What is your advice in advising customers on the color variation?
There is absolutely no chance you are ever going to get a color match in any of the laminates. That's my advice. They are not a decorative product. They're an industrial product, and unfortunately, even from the same mill, different lots may wind up with different shades, different colors. Not dramatically from the same mill, but you will get variation. And from mill to mill, you will get wide variations. But once again, it's not a decorative material, and your chances of getting a color match are nil. So don't fall into that trap, and it's an easy trap to fall into.
Okay. To improve the tolerance by sanding, is there a specific coarseness or sanding method that works best with thermosets?
You generally want a large, when I say large, a 4-foot wide belt sander, and there are many different grits of sandpaper to use. There are some applications where they want you to get it as smooth as possible. There's other applications where, for instance, they may just want to take off that skin surface that's very glossy so that they can leave something with a little more bite to it so they can glue the phenolic material to some other material. So you really have to ask the customer what it is that they want. But you can get, grits from 40 to 80 to 120 sandpaper, and you can get the different results depending on what you use. Again, you want to make sure you know what the customer is really looking for. One other thing I need to add, when you do sand this material, it does make it much more difficult if somebody wants to print on it, if they want a silk screen on it. The shiny skin surface that comes on the laminate sheets as they come out of the press is wonderful for printing on, very glossy. That resin is cooked against the stainless steel platens, and you get a down it, something like that, it's gonna run on you a little bit. So that's another an area where you got to keep that in mind.
Okay. We just had another question come through. People always ask for G10 material, and like you said in the past, it's automatically been given that they can use FR4 instead. What questions should be asked to clarify in case the customer really does want a true G10?
I would ask if they're looking at a print and exactly what the print calls out. Is it giving you any other information as far as a NEMA grade or a military specification? That's the best way to get after it. Again, you've just got to ask the customer for more information and nail it down.
Got it. Well, really great questions and great answers. Thank you. Mark has his email up here and his phone number. If anybody thinks of anything after the presentation's over, feel free to reach out to him. Reach out to Rich, and either one will be happy to answer questions for you. I'm going to take this final question that just popped in here, and then we can sign off. But what is the thickest CE sheet manufactured?
Pretty much, you could make them as thick as you want. One of the problems is the ability to saw cut them after that. Domestically, the thickest sheet we generally see is right around 6 inches. If you want something thicker than that, you're almost always going to have to make it up of 2 smaller sheets and either mechanically or glue them, bond them together somehow. Overseas, I think you can get maybe up to 8-inch thick sheets for specialty applications, but once again, it's tough to find somebody with a big enough saw to cut through those, and domestically 6 inches is probably all you're going to see. And I would just like to add that I thought the quality of the questions was absolutely outstanding. So
yeah, these were great questions. So to everyone who
so we greatly appreciate it.
Best ever.
Yeah, definitely. Okay, well, thank you so much. And a couple of people have asked me if they're going to get the slides, and you will get a copy of the slides. You're going to receive a survey here in about an hour. If you can complete that survey for us, it gives Mark and Rich great feedback. It tells IAPD kind of the direction of webinars that you'd like to see. So please complete that for us. It's very brief. And at the end of it, there is a link to be able to download today's slides. And then I'll also get the webinar recording up on IAPD's YouTube channel. I'll send an email out whenever that's up there. So if you want to share it with people in the office, or just replay it and kind of hear these great questions and answers again that Mark and Rich gave us. So just want to thank you two for being our presenters today. We appreciated having you, and thank everyone for being on the call. IAPD does hold monthly webinars, so check back on our website and Be sure